Hello everybody, today we'll talk about Doppler effect. So the Doppler effect or Doppler shift is the apparent change in frequency of sound when there is a relative motion between the source of sound and the observer. Austrian physicist Christian Doppler described this phenomenon in 1842. Now the perceived frequency can be greater, lesser, or stay the same based on different conditions. And Doppler effect is applicable to both sound waves and light or electromagnetic waves. However, we're going to stick to sound waves in this topic. So what do we need for this Doppler phenomenon? So first we need a source, which is a source of sound, let's say an ambulance, and then a receiver. A receiver is someone who perceives those sound waves, in this case an observer who's standing on the road. And the sound is the energy emitted by the source, so the ambulance siren is the sound in this case. And finally the medium, so the medium through which the sound waves travel. Sound waves cannot travel through vacuum, they need a medium, and in this case the medium is air. So this is a setup of the Doppler effect phenomenon. So you have an observer standing in the middle of the road, and then on the left side you have the ambulance, which is approaching the observer, and on the right side the same ambulance is receding away from the observer. So we're going to check this more in greater detail. So first, let's say the ambulance is stationary, and then it emits a siren. Now, as long as both are stationary, there's going to be no change in perceived frequencies. The observer is going to register the sound as is. We'll see why with equations later in this video. Now, let's say the ambulance started moving and it's still playing the sound. What happens? So this is a case when the source is approaching the stationary observer. When the source moves from point A, which is the initial position of the ambulance, and heading toward point B, so it's going to approach the observer, each successive crest is emitted from a position closer to the observer than the previous wave. So each wave takes slightly lesser time to reach the observer than the previous wave. So when you say lesser time, it's sort of getting compressed. So the time between the arrivals of the successive crests and the observer is reduced. So when you reduce the time, so what happens is the wave fronts are bunched together, and it's like the wavelength is getting shorter, which means the frequency is increasing. So the sound registered by the observer is pitch shifted up due to the Doppler effect. So as you can see here, as the ambulance approaches, the wave fronts are getting compressed and the frequency increases. So the end result is the observer is going to perceive a high-pitched sound than the original frequency of the sound. Now the next case is a receding source. When the source moves away from the observer, each wave is emitted from a position farther from the observer than the previous wave. So as a result, the arrival time between the successive wave is increased, or in other words, the wave fronts are spread out. And when they are spread out, the wavelength is more, which means the frequency is less. So the sound registered is pitch shifted down due to Doppler effect. So when the ambulance is moving away or receding away from the observer, the perceived frequency is lower than what it actually is. So what are the insights? Compared to the original frequency, the apparent frequency is perceived differently. Either it's perceived higher or lower or same. It depends on different conditions. Sound waves need a medium to propagate. So in this case, the medium is air. So air is an example of medium. And speed of sound is an important factor in the Doppler effect calculation, and hence medium is important. Now, speed of sound is different in air or in water, but we're restricting in this example to air, so we know the speed of sound in air is 343 meters per second, and we will not consider the influence of wind in our calculations. Here's the equation which describes the relation between the actual and the apparent frequency. So F is the apparent or the perceived frequency of the sound wave, F0 is the original frequency of the sound wave, C is the velocity of sound in air, which I've approximated to 340 meters per second, V0 is the velocity of the observer, as in the person, and Vs is the velocity of source. So let's talk about several different cases from this equation. We can actually generate 8 such cases and explicitly observe how the Doppler effect behaves in each of those cases. So this is the first case. This is a very trivial case, but I still wanted to explicitly state it out. So this is the case when both the source and the observer are stationary. So it's like there is no motion at all between those two. So this is like a stationary ambulance switching on the siren and a stationary observer perceiving the sound waves emitted by the siren. So in this case, if you plug in the values, since both of their velocities are 0, the apparent frequency or the perceived frequency is exactly same as the original frequency. This is true because Doppler effect demands relative motion between the source and the observer. Since there is no motion between the two, there's going to be no Doppler effect. So the next case is interesting. So this is where the source is moving toward the stationary observer. So in this case, the observer is standing still, so his velocity is 0, whereas the source is approaching the observer, so his velocity is not 0. So if you plug in those values, you get that the apparent frequency is greater than the original frequency, which is true because as we saw earlier, when the ambulance is approaching the observer, the wavefronts are compressed and the perceived frequency is higher than it actually is. Now the same is true for when the source is moving away from the observer. So in this case, again, the observer is stationary, so it has 0 velocity and the source is non-zero. But then you plug in the equation values and you get that the apparent frequency or the perceived frequency is less than the original frequency. This is true because when the source is moving away, the wavefronts are going to stretch out, so the perceived frequency is lower than it actually is. So the next case is the source is stationary, whereas the observer is moving. So in this case, the observer is moving, or let's say running toward a stationary source. So since the source is stationary, the velocity of the source is 0, whereas the velocity of the observer is non-zero. If you plug in the equations, you still get the same thing, which is the apparent frequency is greater than the original frequency. So which means if a person is running toward a source, he's going to perceive slightly higher frequency than it actually is. So the next case involves again the same. The observer is moving away from the stationary source. So the source is stationary, whereas the observer is running away from that source. And in this case, he's going to perceive lesser frequency than it actually is. The next two cases are interesting because they involve both the source and observer in motion. So in this case, the source and observer are moving toward each other. So none of their velocities are 0, and there is relative motion between the two. So there's going to be Doppler effect, but we don't know what the actual outcome is going to be, but we know for sure that the apparent frequency is not equal to the original frequency. It depends on the velocity of the source and the observer. So if you know the values of the velocity of source and observer, you plug it in, and then finally you're going to get some value, which not necessarily is going to equal, it's going to be greater or lesser. The next case is again the same. The source and observer are now moving away from each other instead of moving toward each other. Again, the apparent frequency is not necessarily equal to the original frequency. It's going to change. It's going to depend totally on the velocity of the source and the observer. The next case is also can be regarded as a trivial case because the source and the observer are moving, but they are moving at the same speed. So although they both are in motion, they both have non-zero velocity, there is still no relative motion between them. So it's like, for example, the source is following the observer. Both are moving at like 50 kmph and both are moving, one is following the other. So if you plug in the values, you can see that the velocities cancel out and you get the final result is the apparent frequency same as the original frequency. This is true because Doppler effect demands relative motion between the source and the observer. And in this case, although they both are in motion, but there is no relative motion between the two, there's going to be no Doppler effect. So this is a pass-by noise of an ambulance. I'm demonstrating Doppler effect, so it's better you wear a headphone so as to perceive the three-dimensionality of the Doppler effect. Let's hear it. So I hope you heard the pitch up and the pitch down of the ambulance siren sound. So I just performed a Doppler experiment in-house. So I just took a sound source such as a portable tone generator and the source generates 1 kHz pure tone. Consider a stationary observer, which is in this case an audio recorder, and the source is moved by hand from left to right or right to left in front of the audio recorder, and the audio recorder records the entire audio event. So the setups look something like this. So I have an audio recorder. Basically, it's just a mobile phone, and the tone generator also is a mobile phone. So the audio recorder is going to record the sound, whereas the tone generator would be swept from left to right by myself, by my hand. So I'll be sweeping it at like a random velocity, and then the goal is to check if the actual sound captured by the audio recorder, which is then processed, is there a Doppler effect in that sound. Let's see. So here's a reference 1 kHz sound wave. In fact, this is a case where I'm like, playing the tone generator 1 kilohertz. I'm like actually keeping the tone generator right here so that there is no relative motion between this audio recorder and the tone generator, and then playing back 1 kilohertz so that it's captured by this audio recorder. And it looks something like this. There's going to be no Doppler effect because there's no relative motion between the two. Let's hear it anyway. So as you heard, it's just a simple pure tone, and which when processed with the spectrograph, it also results here. We can see the peak at 1 kilohertz. Now let's do some motion, relative motion between the audio recorder and the tone generator. So I just swept past from left to right and right to left in front of the audio recorder, and you can hear or perceive the Doppler effect. You see that when, the regions in between the sweeps, these are the regions when I was still holding the tone generator stationary, there was no motion, but these are the regions where I was actually in motion. So like I was moving from left to right, right to left, and so on. So now let's process this information and see, if we can actually see any apparent frequency, or is it going to be the same 1 kilohertz. So as you can see here, this is a time trace, and I know that this is the region where I was stationary, but then this is where the tone generator was approaching the audio recorder. And let's just, consider that region of the trace and do the processing. And what we know from this cases that we saw, that when the source is approaching a stationary observer, the stationary observer is going to perceive a sound which is higher than it actually is. Higher in frequency. So it is actually evident here that I don't know what velocity with which I move my hand, but I do certainly know that there is some kind of Doppler effect here. So it's like I didn't do any calculation, but then I'm just doing a measurement empirically and determining the answer. So when I do move, when I do consider that trace, I do see that the peak is at 1008 hertz, not 1000 hertz. So there is some minor increase in the perceived frequency. So here you have it. So when you have an approaching source, the perceived frequency is higher than it actually is. In this case, it's 1008 instead of 1000. Now let's do the receding sound analysis. So we take the same trace, and we only consider the part where the tone generator was moving away from the audio recorder. And then you do the analysis. We see that the peak is no longer 1 kilohertz, but rather 993 hertz. Obviously, it has undergone a Doppler shift, so the perceived frequency is lower than it actually is because the sound source is moving away from the stationary observer. So this was the demonstration of the Doppler effect. So here's a graph of apparent versus actual frequency for a set speed of 50. So as you can see here, the green line represents the approaching source, red is the receding source, and obviously the green is above the red because whenever the source is approaching, the frequency is always perceived higher, and when it's receding, the frequency is always perceived lower. So what is the applications of Doppler effect? Well, one of the applications commonly used in everyday life is radar gun. It's on the Doppler effect of light, but still it's Doppler effect. So a radar gun is used to measure the speed of moving objects. The device sends out a narrow beam of radio signal. The signal hits the target and returns back. So there is now relative motion, and the frequency of these reflected waves is higher if the object is approaching the radar and lower if it's receding away from the radar. And the input frequency, reflected frequency, and speed of light are known. You can determine the velocity of the object. So in this case, the target is to determine if somebody is overspeeding. So in that case, we don't know what the velocity of the observer is, considering we are the source aiming the radar gun at them. But we do know the input frequency and reflected frequency and also the speed of light, so we can do the back calculation to determine what is the velocity of the object. So to conclude, the Doppler effect or Doppler shift is the apparent change in frequency of sound when there is relative motion between source and the observer. The perceived frequency can be greater, lesser, stay the same based on different cases. Doppler effect is applicable both for sound waves and light or electromagnetic waves. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.